Hello everyone, welcome to the video solution for instruction 6 for Mechanics of Materials. This instruction corresponds to week 3.7 of Materials, or Learning Unit 8, which is Deflection of Beams. Now the problem that we're going to look at today is no longer in the textbook, so it is important to pay attention if you'd like to understand the setup. We have that the loading on a floor beam used in an airplane is shown in this diagram here. We have to use discontinuity functions and determine the reactions at the supports A and B, and then draw the moment diagram for the beam. So the first step in any problem is to first understand it better by drawing a free body diagram. In this case, I can simply illustrate it by a line. The forces that we have acting on the beam are AY, illustrated here, BY, drawn like this, and a distributed force drawn here. Now we can label these as AY, W, and BY. Furthermore, we also have a reaction force for B in X, as well as a reaction moment in the positive counterclockwise direction. I can therefore define my axes as Y and X positive this way. Now I have that this length is equal to a total of 6 meters, but in this case I shall indicate simply as a total of L, summing up at L over 2 at W. So where do we start? The first thing we do is to take the force and moment equilibriums for this free body diagram. We can first start with the easy one, and that can be the force equilibrium for the forces in the x direction. We know that to be equal to 0, and the only contributing force is bx, and therefore we know bx is equal to 0. We can also write the force equilibrium in y, positive upwards, equal to 0. And we know that that equals to AY plus BY minus the contribution of this distributed force, which is just W times the length that it acts on, which is L over 2. Finally, we can also do a moment equilibrium at B counterclockwise positive. The contributions to that are the internal moment at B. The contribution due to AY is negative, and the contribution to W is positive. So we know therefore that MB minus AY times L plus the force acting at W, which is W times L over 2, times the moment arm in which it acts on, which is L over 4. Now that we have our force equilibriums, as the equation implies, we have to use this, the deflection equations to find out what the reaction forces are, as this is a 2-equation, 3 unknown system. So we can write out our moment from the Macaulay stump functions. So the moment from the Macaulay step functions follows as such. We have a moment at x, where x is defined as starting at this point and progressing towards here. So the moment is therefore defined by the contribution of y, which is ay times x minus 0 because it is present from the very beginning, minus W over 2 times x minus L over 2 squared, as it is a distributed force contribution. We can then plug these in to the discontinuity equations, which is that the second derivative of v with respect to x is equal to the moment at x, the moment at any point x. So we can write this as ay, where the x minus 0 becomes simply x, minus w over 2 times x minus L over 2 squared. I can then find the next step corresponding to dv dx by doing a simple integration. I get that ay times the integral of x, which is x squared over 2, minus w over 2 times the integral of x minus L over 2 squared, which is simply that same function cubed divided by 3, plus an integration constant that we'll call c1. And then the final step follows from another integration, and we will say that this equals to ay times the integral of x squared divided by 2, which is x cubed divided by 6, minus w over 2 times the integral of x minus L over 2 cubed, which is then x minus L over 2 to the 4th divided by 12, plus the integral of c1, which is c1 times x, plus another integration constant c2. Now we know that these are the equations that describe the deflection of the beam. However, the two integration constants are still unknown, and therefore we have to look at the boundary conditions to be able to solve it. So what boundary conditions do we know? If we scroll back to the free body diagram, we know that the beam at point A and point B has to not move. So we know that the v at both of those points is equal to 0. We also know that at B it is attached to a rigid wall, and therefore the angle at B has to be equal to 0. If I can summarize this, I say that we have v at x at 0 is equal to 0, v at L is equal to 0, as well as dv dt, which is the angle at L, is also equal to 0. So let's look at the equations that we can come up from this. If we plug it back into this into the equations, I can look at this one and write that 0 is equal to 0 minus 0 plus c1 times 0 plus c2. This therefore means that c2 is equal to 0. If I write the function for v at L, I know that v, which is, well, 0, is equal to ay times L cubed over 6 minus w over 2 times x minus L over 2, where x is equal to L, so therefore L over 2 to the 4th divided by 12 plus c1 times L. And then my final boundary condition gives me that 0 is equal to, using this equation, ay times L squared over 2 minus w over 2 times L over 2 cubed divided by 3 plus c1. Now we have two equations right here. Let's label them 1 and 2. If I write these out in a nicer form, I get that equation 1 can be written as ay L cubed divided by 6 minus w L to the 4th divided by 348 plus c1 times L. and that equals to 0. Now, I also have equation 2, which can be written out as ay l squared divided by 2 minus wl to the cubed divided by 48 plus c1 is equal to 0. And my bad, this is actually 384. So we can see, as these are both the governing equations, we can then solve them simultaneously. I can divide the first equation by L to obtain that this L drops out from C1, the L to the fourth becomes L cubed, and the L cubed becomes L squared. I can then also multiply the equation by 3, and it still be equal to 0, thereby becoming ay L squared divided by 2, and WL cubed divided by 128, as well as C1 becoming 3 times C1. Now I have two equations which are very similar, and I can subtract them to obtain my final solution. The first two cancel out, so I get 0. The second term becomes WL cubed times negative 1 over 128 plus, which is minus 1 over 48, plus 3 minus 1 C1, which is just 2 times C1, and that equals to 0. If I then solve this system for C1, I get that C1 must be equal to negative 5 over 768 WL cubed. Now that I know C1, I can plug it back into the second equation right here to obtain ay. I therefore know that ay L squared over 2 minus WL cubed over 48 minus 5 over 768 WL cubed is equal to 0. If I then would solve this for ay, I get that ay must be equal to 7 over 128 WL. So now that we found our ay, our initial force equilibrium equations become a system of two equations and two unknowns. Therefore, I can plug them back in to find the remaining unknowns. From the force equilibrium in the y direction, I obtained the following relation. It was that ay plus by minus wl divided by 2 must be equal to 0. As I know ay, I can then rewrite this equation for by, which then means that wl over 2 minus ay, which is 7 over 128 wl. In here, to make the fractions nicer, I can multiply both sides by 64, both the numerator and the denominator by 64, which then becomes 64 over 128, thereby giving me that by is equal to 57 over 128 WL. Finally, to solve for my last unknown, I can look at the momentum balance for the beam, and I obtained from that equation that mb minus ay times L plus WL over 8 L squared is equal to 0. Writing this in terms of mb, I can then say that mb is equal to ay times L minus WL squared divided by 8. Now, as Ly is equal to 7 over 128 times WL times L, which makes WL squared, minus WL squared over 8. And we can then say, well, multiply both sides by 16. So this becomes 16 over 128 and MB is written as negative 9 over 128 W squared. I can then, once I have found all of these relations for AY, BY, and MB in variable form, I can then use the initial condition in the initial setup of the problem to solve for these values. I saw that AY was equal to 7 over 128 times W times L, where W in this case is equal to 5,400 newtons per meter and L is equal to 6. I therefore get that AY is equal to 1.77 kilonewtons. To solve for BY, I had that it equals to 57 over 128 times 5,400 times 6, which is just W times L, and that therefore equals to 14.4 kilonewtons. Finally, I get the equation for MB, which was just negative 9 over 128 times W, which is 5,400, times L squared, which is 6 squared. And therefore get that it equals to negative 13.7 kilonewtons. Now that we have these forces, we can draw the moment diagram. But before we draw the moment diagram, we first have to draw the shear diagram. If I have all these forces to the left here, I can draw my shear diagram as such, where this is the shear force in kilonewtons. So if I know, if I look at the free body diagram, we see that there is a initial force AY here, and then a distributed force at L over 2. I can then go to my shear force diagram and simply draw a straight line at 1.77 kilonewtons until the point L over 2. And this is equivalent to 1.77 kilonewtons. At L over 2, the slope then becomes negative 5.4 kilonewtons per meter, and this goes down linearly until a value of 14.4, negative 14.4 kilonewtons at B. I can then, from this shear force diagram, draw a moment diagram. This moment diagram will therefore look something like this. This is the moment in kilonewton meters. From the value of 1.77 kilonewtons, I know that my moment will increase linearly until L over 2, until it will reach a certain value here. Now this value, m at L over 2, can be calculated simply by the area under the graph for the shear force diagram. So this will simply be 1.77 kilonewtons times L over 2, which is 3 meters, resulting in approximately 5.4 kilonewton meters. So this is at 5.2 5.3 kilonewton meters. Now, we see that that is, however, not the maximum point, because the maximum point of a moment diagram occurs when the shear force is equal to 0. We know that this distance is equivalent to 1.77 kilonewtons divided by the slope, which is 5.4 kilonewtons, obtaining that this is approximately 0.33 meters. So the moment at that point, we'll call that moment max, is equal to the moment at L over 2 plus the contribution of that little part, which is a triangle that is described by 1/2 times 0.33 times 1.77, giving us maximum at 5.6 kilonewton meters, slightly after L over 2. Finally, we have that there is a linear decrease in the shear force diagram, leading to a quadratic decrease in the moment diagram, giving a slope something like this. Of course, at this point, you have a value of, well, the contribution of this triangle, which is then equal to, well, m at b, and it will be 5.6 kilonewton meters plus 1/2 times 3 minus 0.33 times 5.4, or 14.4 negative. This then results in a total of negative 13.7 kilonewton meters, which we can indicate here, and thus our moment diagram is finished drawing. In case you have horrible skills in drawing just like me, you can indicate that this slope is quadratic by simply giving it a label. Thank you for watching, and I hope that this was helpful. If you have any questions, please feel free to join the instruction session Q&As, which happen at the normal instruction times on Thursday and Friday.